Right now, roughly 12.5 billion miles from where you're sitting, a 49-year-old antenna is picking up a faint radio hum, a frequency measured in thousands of cycles per second. Arriving from a region of space no human instrument had ever directly sampled before this exact spacecraft got there. It isn't coming from Earth. It isn't coming from anywhere inside our solar system at all. It is coming from the plasma that fills the actual gap between stars. And the machine listening to it, Voyager 2, is one of only 2 objects our species has ever built that could possibly be in a position to hear it. There's no dramatic control room moment attached to this, no team of scientists leaping out of their chairs. The signal arrives quietly, embedded in a routine data download, sitting in a stream of numbers that most people would scroll straight past without a second glance. But buried inside that unglamorous stream of number is a genuine physical echo of something that happened at our own sun months or years earlier, and the fact that we can hear it at all from a spacecraft this old, this far away, is stranger than almost anything a screenwriter could have invented. This is the real story behind that signal, what it actually is, why it keeps showing up years apart instead of constantly, and why solar physicists are watching this particular spacecraft especially closely again right now in 2026 for reasons that have everything to do with what our own sun has been doing lately. Let's start with the machine itself, because Voyager 2's story gets overshadowed constantly by its more famous Twin A. And that's genuinely a shame, because in some ways Voyager 2 is the more remarkable spacecraft of the two. It launched on August 20th, 1977, 16 days before Voyager 1, from Cape Canaveral, riding a slower trajectory that would eventually let it do something no other spacecraft in history has ever managed. In the late 1960s, an aerospace engineer named Gary Flandreau, working as a summer intern at NASA's Jet Propulsion Laboratory, noticed something in his orbital calculations. Jupiter, Saturn, Uranus, and Neptune were all going to align on the same side of the solar system in the late 1970s, a geometric coincidence that happens roughly once every 176 years. Using the gravity of each planet to slingshot toward the next, a single spacecraft could theoretically visit all 4 giant planets in one continuous mission instead of requiring 4 separate ones. NASA built 2 spacecraft to attempt exactly that. Voyager 1 took the faster route, prioritizing a close pass of Saturn's moon Titan, which meant its trajectory only allowed for 2 planetary flybys, Jupiter and Saturn, before it was flung out of the plane of the solar system entirely. Voyager 2 took the patient route, the one that kept the full grand tour alive. It reached Jupiter in 1979, discovering active volcanoes on the moon Io and threading a path through the planet's radiation belts that would have fried a less carefully shielded spacecraft. It reached Saturn in 1981, capturing detailed images of the planet's rings and moons before using Saturn's own gravity to bend its trajectory onward, toward a destination no spacecraft had ever been sent to reach on purpose. And then it kept going, where nothing else has gone before or since. Uranus in 1986 and Neptune in 1989. To this day, nearly 4 decades later, Voyager 2 remains the only spacecraft in human history to have ever visited either of those 2 outer ice giants. Nothing else is even scheduled to try again anytime soon, which means every photograph, every measurement, every scrap of data we currently have about Uranus and Neptune up close still comes from a single flyby each, performed by the same aging spacecraft now listening for signals in interstellar space. That patient 4-planet trajectory came at a cost, though. It meant Voyager 2 reached interstellar space considerably later than its sibling. Voyager 1 crossed the heliopause, the outer boundary of the Sun's protective bubble, in 2012. Voyager 2 didn't cross that same threshold until November 5th, 2018, 6 years behind, a gap that exists purely because of the extra years it spent looping past Uranus, and Neptune first. That 6-year delay turned out to be scientifically useful in its own right, though, because it meant Voyager 2 crossed the heliopause at a completely different point on its surface than Voyager 1 had, giving scientists their first opportunity to compare 2 independent crossings of the same boundary at 2 different locations, separated by the better part of a decade. But when it finally did cross, something interesting happened. Researchers at the University of Iowa, using an instrument on Voyager 2 built specifically to measure plasma waves, detected what they described as a definitive jump in plasma density right at that boundary, evidence that Voyager 2 had genuinely left the hot, thin plasma of the solar wind behind and entered the cooler, denser plasma that fills interstellar space. On January 30th, 2019, at a distance of roughly 119.5 astronomical units from the Sun, that instrument recorded an electron density of about 0.039 particles per cubic centimeter, a jump of somewhere around 20 times the density found just inside the boundary. It was, almost eerily, close to the very same density Voyager 1 had measured when it made its own crossing 6 years earlier. 2 independent confirmations of the same physical boundary, recorded by 2 separate spacecraft in 2 completely different parts of the sky. which gave researchers real confidence that they weren't just looking at some local quirk unique to one direction of the solar system, but at a genuine consistent feature of the boundary itself. Here's where the story gets genuinely interesting, and it's a detail that almost never makes it into the more popular retellings of this mission. Voyager 1's dedicated plasma science instrument, the one designed to directly measure the density and speed of charged particles around it, actually failed decades ago, sometime around 1980, not long after its Saturn flyby. For years, that meant Voyager 1 couldn't directly sense plasma density at all. It had to infer it indirectly, using its separate plasma wave instrument to listen for a very specific kind of radio emission produced when the local plasma is disturbed, then working backward mathematically to calculate what density of plasma would have to be present to produce a signal at that particular frequency. Voyager 2's equivalent plasma instrument, remarkably, still works. It's the only one of the two spacecraft still capable of measuring interstellar plasma density directly, without having to go through that indirect calculation. Which means that in a very real, literal sense, right now, this second, less famous spacecraft is our only direct sensor sitting in interstellar space. Everything we know about that environment from Voyager 1 has to be inferred. Everything we know from Voyager 2 can, at least for this one measurement, simply be read. So what is this frequency people keep hearing about exactly? And why does it come and go instead of humming along constantly? Here's the physics, and it's genuinely elegant once you see how it fits together. Every so often, our sun releases a violent eruption of charged particles and magnetic energy called a coronal mass ejection, essentially a massive burst of solar material thrown outward in every direction, sometimes carrying more energy than 1 billion hydrogen bombs detonated at once. That burst travels outward through the solar system, taking anywhere from a few days to reach Earth's orbit to well over a year to reach the outer edges of the heliosphere, depending on its initial speed and how much material it's pushing ahead of it. Eventually, it crosses the heliopause and slams into the surrounding interstellar plasma, like a wave hitting a shoreline. Except this. Shoreline sits tens of billions of miles from where it started. When that shock wave reaches the electrons sitting in that interstellar plasma, it doesn't just push them out of the way. It makes them ring, briefly oscillating back and forth at a very specific, very telling frequency. The same basic principle as striking a bell and listening to the note it produces. Except in this case, the bell is an invisible cloud of charged particles floating in the vacuum between stars, and the note comes back to us not as sound, but as a faint burst of radio frequency energy. That frequency depends directly on how densely packed those electrons happen to be in that particular region of space. Voyager 2's plasma wave instrument is sensitive enough to catch that ringing from tens of billions of miles away, and by measuring the exact frequency of the oscillation, scientists can calculate the electron density of the interstellar plasma the shock wave just passed through without ever needing to physically sample it any other way. These events, called electron plasma oscillations, don't happen constantly because the shock waves that trigger them don't happen constantly either. It takes months, sometimes over a year, for a solar eruption powerful enough to trigger one of these events to actually travel all the way out to where Voyager 2 currently sits, weakening and spreading out the farther it travels, so that only the strongest eruptions ever arrive, with enough punch left to register clearly against the instrument's own background noise. Since crossing into interstellar space, Voyager 2 has picked up a handful of these events, one shortly after its 2018 crossing, another in mid-2020, a brief one lasting less than a day on May 23, 2021. Recorded at a distance of about 127 astronomical units, and its most recent confirmed detection in November of 2022. Each one gives researchers a fresh, independent data point for the density of interstellar plasma at whatever distance the spacecraft happens to be at when the shockwave arrives, slowly building up a map of how that density changes the farther Voyager 2 travels from the heliopause, one faint ringing tone at a time, sometimes with a year or more of total silence between one detectable event and the next. There's a quiet piece of scientific detective work buried in this pattern that's worth pausing on, because it connects everything happening out at Voyager 2 back to something happening 93 million miles closer to home inside our own sun. The sun runs on an 11-year cycle of rising and falling activity, swinging between a quiet minimum and a violent maximum when sunspots multiply and coronal mass ejections become dramatically more frequent. Researchers studying the pattern of plasma oscillation events detected by both Voyagers noticed something telling. The shockwaves reaching Voyager 1 tended to trace back to eruptions launched during the peak of the sun's activity cycle, while the ones reaching Voyager 2 tended to trace back to eruptions launched closer to solar minimum, the quiet stretch in between. That's not a coincidence baked into the spacecraft. It's simply a reflection of how long it takes a given eruption, launched at a specific point in the solar cycle. To actually travel the tens of billions of miles out to wherever each spacecraft happens to be sitting when the shockwave finally arrives, that detail matters enormously right now in 2026 because of where we currently sit in that 11-year cycle. Solar cycle 25 reached its predicted maximum around the middle of 2025, meaning the Sun has, over roughly the past year, been producing coronal mass ejections at a noticeably higher rate than during the quieter years just before it. Every one of those eruptions is a potential future signal, a burst of solar material now working its way outward through the solar system, due to reach the heliopause and the interstellar plasma beyond it at some point over the following months to years, depending on its speed and the distance it has to cover. That means the increased solar activity astronomers have already recorded closer to home over the past year or so is, quite literally, still in transit right now, somewhere in the vast gap between the Sun and the heliopause on a slow multi-year journey outward toward Njoma, wherever Voyager 2 happens to be by the time it finally arrives. Researchers who track this pattern have explicitly noted that Voyager 2, now sitting somewhere around 140 astronomical units from the Sun, is well within range to keep catching these events as this current wave of solar activity works its way outward, and that the spacecraft could plausibly continue detecting them for years. Yet, provided both the instrument and the aging spacecraft carrying it keep functioning long enough to receive them. It's worth taking a moment to appreciate just how improbable it is that this instrument still works at all. The scientist most responsible for building and interpreting Voyager's plasma wave data, Donald Gurnett of the University of Iowa, spent over 4 decades of his career studying exactly this kind of signal, from Voyager's earliest flybys of Jupiter and Saturn all the way through its historic crossings into interstellar space. He helped design the very instrument now catching these faint interstellar echoes back when the spacecraft carrying it was still being bolted together in a clean room, decades before anyone could say with certainty it would even survive long enough to reach the edge of the solar system, let alone keep working once it got there. He passed away in 2022, the same year Voyager 2 recorded its most recent confirmed plasma oscillation event, having spent essentially his entire scientific life listening to a spacecraft slowly carry his instrument farther from Earth than any human being will travel in several lifetimes. There's something quietly moving about that timing. A scientist and the instrument he built reaching one of their final shared milestones together in the same year. The research he helped pioneer is now carried forward by colleagues including William Kurth, who continues analyzing the same data today, extracting fresh insight from a spacecraft that was never expected to still be transmitting. Usable science this far into the 21st century, using techniques and instincts built up over a career spent listening to exactly this kind of signal long before anyone else fully understood what it meant. Here's what makes all of this more than just an interesting technical curiosity. Every one of these plasma oscillation events, each burst of frequency. Voyager 2 catches from a shock wave, crossing paths with it billions of miles from home, adds another data point to something scientists genuinely did not have any real-world measurements of before these two spacecraft got there. A working physical map of how plasma density actually changes as you move outward through the very local interstellar medium, the region of space our entire solar system happens to be drifting through right now. Before Voyager, every estimate of that density came from models built entirely from indirect evidence gathered here on Earth, telescopes, theoretical calculations, educated extrapolation from the physics of other stars. Never a single direct measurement taken from inside the environment itself. Early measurements suggested that density might be climbing the farther both spacecraft get from the heliopause, almost as if interstellar material were piling up against the outer edge of our solar system's protective bubble the way snow piles up in front of a moving snowplow, compressed and concentrated right where our sun's outward push finally runs out of strength. Nobody fully understands yet whether that increase will keep climbing, level off, or eventually start falling again. Continued detections from Voyager 2, especially as this current stretch of heightened solar activity sends fresh shock waves outward over the next several years, represent one of the only realistic ways left to keep answering that question with real data instead of pure theoretical modeling. Because here's the sobering part of this story that runs underneath everything else. Voyager 2's power supply, like its twins, is slowly and permanently dying, losing a small amount of electrical output every single year as the plutonium powering its onboard generators continues its steady radioactive decay. Engineers have already been forced to shut down several of the spacecraft's scientific instruments permanently, one by one, simply to keep enough power flowing to the ones considered most valuable, weighing each shutdown decision against exactly the kind of trade-off mission planners never wanted to have to make. Which questions get to keep being answered, and which ones simply stop being asked permanently the moment a given instrument goes dark. Some analyses of the mission's long-term power budget suggest that by around 2028, the spacecraft may no longer have enough electricity available to keep any instruments running at all. Every additional plasma oscillation event Voyager 2 manages to catch between now and then, every fresh frequency this current wave of solar activity sends rippling out toward it, is one more piece of a map that nobody currently has any other way of completing, gathered by an instrument. Running on hardware, designed before most of the researchers now studying its data were even born, racing against a countdown clock that has nothing to do with distance and everything to do with a slowly fading power source no repair crew will ever reach in time. So the next time you hear a headline claiming Voyager 2 has picked up some mysterious frequency from beyond our solar system, here's what's actually true, and it's honestly more remarkable than any invented mystery could be. It's not a message, it's not something artificial, and it's not something anyone out there is broadcasting on purpose. It's the physical sound, translated into radio waves, of our own sun's violence reaching all the way out into the space between the stars, ringing the electrons floating, out there like a bell and being caught, faithfully, methodically, by a machine older than the internet itself, still doing exactly the job it was built to do, from a distance no human voice will ever be able to reach. Every one of those distant signals is real physics, all honestly measured, honestly reported, and quietly rewriting what we understand about the exact boundary between everything humanity has ever called home and everything that lies beyond it. If you want more stories like this one, grounded in real, verifiable science instead of manufactured mystery, hit subscribe, turn on notifications, and let me know in the comments whether you'd rather see the next deep dive on Voyager 1's side of this story, or go even further out into what these two spacecraft are still quietly teaching us about the space between the stars.